Hello all. In this lesson we're going to review for the Unit 2B exam, which is mechanics, but it only covers uniform circular motion, dynamics, which is Newton's laws, friction, and Newton's universal gravitation. Alright, so we'll just start with number one. In the diagram below, S is a point on a car tire rotating at a constant rate. So here's point S, it's rotating at a constant rate. The graph that best represents the magnitude of centripetal acceleration of point S as a function of time. So I'll remind you that centripetal acceleration is v squared over r. You'll notice that time is not in this equation, and therefore the best answer is choice 2. Alright, number 2 is right here. We're basing our answers to 2 and 3 on the information in the diagram below. This diagram shows a student seated on a rotating circular platform, holding a 2 kilogram block with a spring scale. The block is 1.2 meters from the center of the platform. So, spring scale, 1.2 meters, 2 kilogram block. The block has a constant speed of 8 meters per second. So, as the block rotates at 8 meters per second in this direction, which statement best describes the block's movement as the platform rotates? So its velocity is directed tangent to the circular path. That's definitely true. The velocity of the block would be going something like that. And it has an inward acceleration, so I think choice 1 is our best answer. What you should remember for this one is that AC and FC, the centripetal force, are both towards the center. So I'll just write in. Number 3, the reading on the spring scale is approximately. Okay, so a spring scale is going to measure forces. So an equation I would recommend using here is Fc equals mv squared over r. And we're looking for force, so we can pretty much go from there. The mass is 2 kilograms, and the velocity is 8 meters per second, but you do need to square that. And the radius is 1.2 meters. And I get a value of 106.7. That would be newtons. So with significant figures, it's going to be choice 3. Alright, so the diagram below shows a 5 kilogram bucket of water being swung in a horizontal circle of 0.7 meter radius at a constant speed of 2 meters per second. They want the centripetal force, so I recommend the same equation we just used, which is Fc is mv squared over r, and the mass is 5 kilograms. The velocity is 2 meters per second. Don't forget to square. And the radius is 0.7 meters. I got as my answer 28.6 newtons. So the best choice is 3. And for number 5, it says, an athlete in a hammer throw event swings a 7 kilogram hammer in a horizontal circle at a constant speed of 12 meters per second. The radius of the hammer's path is 2 meters. And at the position shown, the centripetal force acting on the hammer is directed toward point. Okay, so centripetal force is always towards the center. And at the position shown, which of course is here, the centripetal force would be pointing this way. So point A makes more sense. Okay, we have a roller coaster starts from rest and accelerates due to gravity down a track. The cart starts at a height that enables it to complete a loop in the track. So it's going to go like this. And it says, which diagram best represents the path followed by an object that falls off the cart when the cart is at point D? So if the cart is at point D, then the direction of its velocity and anything in the cart would be this way. In other words, downward. So I'm going to go with choice 1. Number 7, the centers of two 15-kilogram spheres are separated by 3 meters. The magnitude of the gravitational force between the two spheres is. I recommend using the equation for Newton's universal gravitation, which reads that Fg equals big G, m1, m2, over r squared. And the value for big G is 6.67 by 10 to the negative 11. And the two masses are both 15 kilograms. So I'm going to put in 15 squared. And they're separated by a distance of 3 meters. So 3 meters, and that's squared as well. So I always recommend doing the coefficients first. And when you do that, I got 167. And it's going to be times 10 to the something. So that is going to be, in this case, to the negative 11. And that's just because this is the only exponent that was left. But we need to express this in scientific notation. So I'm going to go with 1.67 by 10 to the negative 9 newtons, which would be here. Alright, for number 8, it says a satellite weighs 200 newtons on the surface of Earth. What is its weight at a distance of 1 Earth radius above the surface? So a quick sketch can help a lot here. So this is the Earth, that's an Earth radius, and the satellite weighs 200 newtons when it's on the surface of Earth. So there's my 200 Newton satellite. But when I raise it an extra Earth radius above the surface, the question becomes, what is its weight in newtons now? So if you just use this equation, but without using real numbers, you can see that what's happened to the radius is it went from 1 radius to 2 radii. So I'm going to double the radius. But this is an inverse squared relationship. So this 2 and this square interact and they make a 4. And that means that the value for Fg is actually going to be 1/4 of the original value. And 1/4 of 200 is 50 newtons. Alright, number 9. A 2-kilogram object weighs 19.6 newtons on Earth. If the acceleration due to gravity on Mars is 3.71 meters per second squared, what is the object's mass on Mars? This is a trick question. Object's mass is going to be the same anywhere in the universe, so 2 kilograms. Number 10. A 2-kilogram object is falling freely near Earth's surface. What is the magnitude of the gravitational force that Earth exerts on the object? So gravitational force is the same thing as weight. And weight can be solved for using this equation. So the weight is going to be the mass, which is 2, multiplied by the gravitational acceleration, or the gravitational field strength. And it's going to give you a value of almost 20 newtons. So I'll say almost, or about. And that means the answer is 1. So for number 11, we have a graph that relates weight to mass. And that means that the slope, well, we'll start this way. The slope of any graph, no matter what, is going to be the change in y over the change in x, or the rise over the run. And y in this case is a force, and x is a mass. So that means that what we're getting from a slope here is acceleration. So when they ask me the acceleration, I realize I just need to find a slope. So the rise, I'll just use this point and this point. So between those 2 points, the rise is about 450 newtons, and the run is about 75 newtons. So that slope is 6 meters per second squared, which is here. All right, so for number 12, I apologize that it's somewhat behind my answer for a previous question, but when a 12 Newton horizontal force is applied to a box on a horizontal tabletop, the box remains at rest. The force of static friction acting on the box is. So since the box is at rest, then the frictional force is equal to the applied force. And they told me earlier in the question that the applied force was 12 newtons. So that means the frictional force is 12 newtons. All right, for number 13, we have a box on an inclined plane. And it says as angle theta is increased, the coefficient of kinetic friction. Coefficient of kinetic friction is mu, and specifically it's mu k, kinetic coefficient of friction. But this is determined by the two surfaces that are interacting, and it's not determined by anything else. So it doesn't actually change when theta changes. So I'm going to say remains the same. I'll also point out, though, that in order for the answer to be decrease, then instead of asking about coefficient of friction, it would have had to have asked about frictional force. And in order for the answer to be increase, instead of asking about coefficient of friction, they would have had to ask about normal force. All right, so next question. According to your reference table, approximate coefficients of friction, what is the minimum horizontal force needed to start a 300 Newton steel block on a steel table in motion? So we're going to use a frictional equation, and FF is mu Fn. Let's see, what do they want? They want the force, so we're solving for FF, so this is good. We just need the coefficient of friction between a steel block and a steel table. And I checked my reference table, and the kinetic friction for steel on steel is 0.57, whereas the static friction for steel on steel is 0.74. And since we're starting the steel block moving, then I think we should use static friction. So I'm going to use 0.74 as my coefficient of friction, and the normal force has already been stated actually, because they gave me the weight of the block, and the weight and the normal force are equal. So I'm going to include a 300. The value that I got for frictional force is 222 newtons. So right here, number 4. All right, 15. The magnitude of the momentum of an object is 64 kilogram meters per second. If the velocity of the object is doubled, the magnitude of the momentum of the object will be. So let's just take a look at the equation for momentum, and it says that P equals mv, and they're suggesting that we double the velocity, which means that the momentum will also double. They told me that it was 64 previously, so 64 times 2 yields 128 kilogram meters per second. For number 16, it says, what's the momentum of a 1,200 kilogram car traveling at 15 meters per second due east? So P equals mv again, and in this case the mass is 1,200, and the velocity is 15 meters per second due east. So the magnitude of this momentum is 18,000, and it's going to be east. So we have to do scientific notation. So I'm going to move the decimal 1, 2, 3, 4 places to the left. So that's going to be 1.8 times 10 to the 4th, and the direction is east. So let's see, that means the answer is choice 1. For 17, we have a 6 kilogram block sliding to the east across a horizontal frictionless surface with a momentum of 30 kilogram meters per second, and it strikes an obstacle. The obstacle exerts an impulse of 10 Newton seconds to the west on the block. They want to know the speed of the block. I really love this equation because it tests something that normally isn't tested, which is just a small part of the momentum equations. And it says that impulse is a change in momentum. So since the block was traveling to the east, but the impulse was 10 Newton seconds to the west, then we know how much momentum change there's going to be. The change in momentum is going to be 10 kilogram meters per second. So although we start at 30 kilogram meters per second, we also know that the change in momentum was 10 kilogram meters per second. And the original direction was east, but the impulse is west. So in short, the actual momentum of this object after the collision is no longer 30. Instead, it's going to be 30 minus 10, or 20 kilogram meters per second. Now they do want to know the speed of the collision after the block. So we're going to rely on our trusty old equation, which states that P equals mv. The actual momentum after the collision, as we said, is 20. So I'm going to put a 20 here, and we know that the mass of the block is 6, and we're looking for its speed. So the speed will be 20 over 6, or 3 1/3 meters per second. All right, 18. Which situation will produce the greatest change of momentum for a 1 kilogram cart? This question is a really special type of FAT-MAV question, which basically says that force by change in time is equal to mass by change in velocity. And I say that because choices 1 and 2 are going to be based on the right half of the equation, whereas choices 3 and 4 will be based on the left half. So we know it's a 1 kilogram cart, which means that choice 1 is really asking us to consider m times change in v. So we have the mass of 1, and the change in v is going to be 0 to 3, so 3. And number 2 says the mass is 1, of course, but the change in v is going to be 2, as it goes from 2 to 4. And then for choices 3 and 4, we're going to use F times change in t, and it says we have a net force of 5 for a time of 2 seconds. And for choice 4, it says we have a net force of 10 for a time of 0.5 seconds. So we just need to get some answers for these. Of course, this one is going to be 3 kilogram meters per second. This one is going to be 2 kilogram meters per second. This one is 10, so far it's the winner. Technically it would be Newton seconds, but either of these units is fine. And this one is going to be 5. So the winner is choice 3, applying a net force of 5 newtons for 2 seconds. So number 19. We have a 3 kilogram steel block at rest on a frictionless horizontal surface, and a 1 kilogram lump of clay is propelled horizontally at 6 meters per second toward the block as shown in the diagram below. Upon collision, the clay and steel block stick together and move to the right with a speed of blank. So this is a momentum question, which is going to rely on the equation P before is P after. But we're going to have to consider this an inelastic collision, and I'm going to need some space, so I'm going to move down here. So we're going to start out with MA VIA plus MB VIB, and it's going to give us they're going to stick together upon collision, so I'm going to say MA plus MB, and they'll have only one speed, so I'll say VF. And we are looking for VF, so I'm going to rearrange that now. So I just divided ma plus mb on both sides, and I got this new form for the equation. And at this point, I need to just plug in values and solve. So I chose the clay to be object A, and so I have 1 times its initial speed of 6, and I'm adding that to the mass of the still block, which was actually at rest at the beginning, and then I added the two masses together for the denominator. And I am going to get a value of 1.5 as my final answer, and that would be to the right, but it says so in the question, so we don't need to write that. So for number 20, it says a half kilogram or a 0.05 kilogram bullet is fired from a 4 kilogram rifle, which is at rest. So actually they're both at rest to start with. If the bullet leaves the rifle with a momentum having a magnitude of 20 kilogram meters per second, the rifle will recoil with a momentum having a magnitude of. So while this certainly sounds like it's a momentum question that's going to involve mathematics to solve for the answer, it actually isn't. It's relying on a very basic equation on your reference table that says that p before is p after. Now, at the beginning of this question, we had a bullet inside a rifle that was at rest. So that means everything was at rest, and since p equals mv, and v is 0 in this case, then momentum for the bullet and the rifle before it's shot is 0. So we know for a fact that the momentum of the system before the firing of the bullet was 0. That means that the momentum afterwards also has to be 0. But they told us that the bullet has a momentum of 20 kilogram meters per second after the firing. But in order for the whole system to have a momentum of 0 to match the initial conditions, then that means that the rifle must have a momentum of negative 20 kilogram meters per second. So we know that positives and negatives stand in for directions, and since the bullet was moving one direction, the rifle will go back the other direction, but it'll be the same magnitude. So 20 kilogram meters per second. So for 21, ball A has a mass of 5 kilograms, and it's moving at a speed of 20 meters per second, but it collides with ball B of unknown mass, moving at 10 meters per second in the same direction. After the collision, ball A moves at 10 meters per second, and ball B moves at 15, both still in the same direction. What's the mass of ball B? So one reason why I don't recommend solving this equation using that MA VIA plus MB VIB equals MA VFA plus MB VFB is because the term MB, or mass of ball B, is going to reoccur more than once in the equation. It'll be twice in that equation. So that would make the algebra a lot more difficult. And what I suggest is adjusting our thinking and realizing that we actually know everything for ball A. We know ball A's mass and its original speed, and we also know its final speed. So if we can solve for the change in momentum for A, then we can realize that it's also going to be equal to the change in momentum for B. And the reason for that is because momentum is conserved, and the only two things in this system are ball A and ball B. So their changes in momentum will be equal. And then using the change in momentum for B, I'll be able to solve for its mass. So, that said, I'm going to start solving for the change in momentum for A. And I think that a good equation would look like this, that the mass of A times the change in V of A would be equal to the mass of B times the change in V of B. So let's start looking for MB from here. Divide both sides by change in VB. So from the question, I know that the mass of A is 5, and it started at 20 meters per second and ended at 10, so its change in speed is 10. For the change in VB, it started at 10 meters per second but ended at 15, so its change in speed is 5. So 5 times 10 is 50, and 50 divided by 5 would be 10, which means that the mass of ball B must be 10 kilograms. A 1.2 kilogram block and a 1.8 kilogram block are initially at rest on a frictionless horizontal surface. When a compressed spring between the blocks is released, the 1.8 kilogram block moves to the right at 2 meters per second as shown. Using a similar concept as question 21, I know that the momentum of block A and block B will have to be equal when the spring is released. And the reason for that is because P before is P after, and the momentum before the spring is released is definitely 0, considering both of the blocks are at rest. So I know that the momentum of A has to be equal to the momentum of B, and you can sort of just show that by saying that A minus B will give you 0. So what we're really saying here is that the momentum of A is equal to the momentum of B, or that MAVA is equal to MBVB. We're looking for the speed of the 1.2 kilogram block, so I'll say this one is A and I'll say this one's B. And so we're looking for the speed of A. So that means that VA is MB VB over MA, and VA is, let's see, MB is going to be 1.8. The velocity of B is 2, and the mass of A is 1.2. After solving, I got a value of 3 meters per second, so choice 3. So to do number 23, we have gravitational force F between objects A and B separated by distance r, and we are going to double mass A, and we're going to triple r, and they want to know what's the new gravitational force between A and B. So this question is going to be best solved using the universal equation for gravitation. And it does say that we are going to double mass A, and we are going to triple r. So the effect that doubling mass A would have on Fg is it's a direct relationship, so I'm going to put a 2 there. But this 3 is an inverse square with the Fg, so we have to square the 3, that's going to be a 9, and it's in the denominator, so it's actually going to be 1/9 of the original value. And of course 1/9 times 2, F is going to be 2F over 9. So choice 1 is the best answer for that question. Alright, 24. An astronaut weighs 800 newtons on the surface of Earth. What's the weight of the astronaut this many meters above the surface of the Earth? You can start with a sketch of the Earth. Here's an Earth radius, and we'll put the astronaut here, and he weighs 800 newtons. So I just checked my reference table, and the mean radius of Earth is 6.37 by 10 to the 6 meters. So that means that if you raise the astronaut another 6.37 by 10 to the 6 meters, what you're really doing is you're raising it another Earth radius. So he or she is now at 2 Earth radii. So we can use our equation that says Fg equals big G m1 m2 over r squared, and we can use it conceptually rather than mathematically. So we're now at 2 Earth radii. 2 squared is going to be 1 over 4 as our effect on Fg, and 1/4 of 800 is 200, and that is choice 2. Okay, for 25. A different force is applied to each of 4 1-kilogram blocks to slide them across a uniform steel surface at constant speed. So since they're moving at constant speed, I know that the applied force is equal to the frictional force. And in which diagram is the coefficient of friction the smallest? So since each of these is a 1-kilogram block, they all are experiencing the same normal force because they all have the same weight. So when I take a look at this equation for friction, the one that says Ff is mu Fn, they all have the same Fn, so in essence, I get to ignore it. And I'm really examining the link between frictional force and coefficient of friction. So the applied force is going to be equal to the frictional force, right? So what I'm looking at the link between these two by looking at these values here. So we have an applied force of 5, one of 2, one of 3, and one of 4. And we're essentially saying that there's a direct relationship between the frictional force and the coefficient. So the one that's going to be smallest is going to be the one, in this case, that has the smallest frictional force, which is, let's see, choice 2. And again, the reason is because the frictional force is equal to the applied force for that block. (26) Jill is pulling a 200 Newton sled through snow at constant velocity. So I know that Ff is going to be equal to Fap. Using a horizontal force of 10 newtons. So what is the kinetic coefficient of friction of the sled on the snow? So let's use this equation as well. Ff says mu Fn. And we're looking for mu in this case. So mu is Ff over Fn. And the frictional force is equal to the applied force since we're moving at constant speed. So the applied force was 10 newtons, so that's also the frictional force. And the weight of the sled is 200 newtons, which means that that's going to be equal to the normal force. And 10 over 200 is 0.05. No unit, because it's a coefficient of friction. Okay, so an amusement park ride moves a rider at a constant speed of 14 meters per second in a horizontal circular path of radius 10 meters. What is the rider's centripetal acceleration in terms of g, the acceleration due to gravity? G is 9.81 meters per second squared. But what we're going to do is we're just going to solve this one normally, and then we'll see what our answer will be some multiple of this value. And then we'll figure out what multiple it is, and then we'll be able to say it's either 1g or 2g or 3g or 0g. So let's use the equation AC is v squared over r, since this guy's moving in a circle, and therefore we would describe his acceleration in terms of circular motion. And his velocity was 14 meters per second, which we will need to square. And the radius was 10 meters. So what I got as the magnitude of his acceleration is going to be 19.6 meters per second squared towards the center of his circular path, but they want to know in terms of g how much this is. So you just need to make a ratio, and we can do 19.6 over 9.81, which is the acceleration at g, and you'll get a value of 2. So that means that we're at 2g, or 2 Earth accelerations. 28. A 1,000 kilogram car is driven clockwise around a flat circular track of radius 25 meters. The speed of the car is a constant 5 meters per second. At the instance shown in the diagram, the car's centripetal acceleration is directed. Aha, this is not a math question. The centripetal acceleration will always be directed towards the center of the circle, so that would be toward E in that diagram. An object traveling with uniform circular motion has a centripetal acceleration due to the change in which of these values. So when objects travel in uniform circular motion, their speed is constant. That means that they're moving at constant speed, they're not changing their speed, they're not accelerating at least tangentially to the circle. However, you know they're accelerating towards the center of the circle, and that is the root cause of the object changing its direction at every moment. That's what moving in a circular path means, is that you are constantly changing your direction. So that's why the answer to this question is 2. It's not the speed that changes to give it an acceleration, it's the direction that changes that gives it acceleration. And lastly, on this page, a ball of mass m at the end of a string is swinging in a horizontal circular path of radius r at constant speed v. What combination of changes would require the greatest increase in the centripetal force acting on the ball? So we can use this equation, which isn't on your reference table, but it's made of pieces that are on your reference table. And it says that we have a ball, it's of mass m, r, and v. Okay, so we'll just leave all that alone. But the answer choices are telling you to see how they would give you the largest increase in F. And I can tell you right away that you shouldn't consider 3 or 4 because they're halving V. And if you put a half in front of this V, it's going to square it and it's going to make it a 1/4, and it's going to really drop the FC. So only 1 and 2 are still in the running, and the difference between them is doubling R and halving R. So if I double R, if I put a 2 here, that's going to halve the FC. But if I halve the R, I'll show you that one. When you put a 1/2 in the denominator, it's the same as doubling the FC. And when you combine that with the doubling of V, so I'm going to put a 2 there, 2 squared is 4. So overall, this has a value of octupling FC, so it's definitely choice 2 for this question. Okay, so Io is one of Jupiter's moons, and Io is slightly larger than our own moon, and the mass of Io is 8.93 by 10 to the 22 kilograms, and the mass of Jupiter is 1.90 by 10 to the 27 kilograms. The distance between the center of Io and the center of Jupiter is 4.22 by 10 to the 8 meters. They give you all this data because it's not on your reference table. So we want to calculate the magnitude of the gravitational force of attraction between Jupiter and Io, and we would use, of course, this equation. Fg is big G, m1, m2 over r squared. But we also must calculate the magnitude of the acceleration of Io. And the best way to do that one is to use the very simple equation, centripetal force is equal to mass times centripetal acceleration. And I have to use this equation because the planet will be circling Jupiter, or excuse me, the moon will be circling Jupiter, so it's described by circular motion. And I also am just going to go ahead and preview this part for you. The gravitational force of attraction will be equal to the centripetal force. So we're going to find a value for Fg, and I'll reuse that value for Fc. All right, let's get to it. So the value for G is 6.67 times 10 to the negative 11. But of course, I'll do the coefficient separately from the other parts. And the mass of Io is 8.93 times 10 to the 22 kilograms. And the mass of Jupiter is 1.90 times 10 to the 27 kilograms. The mass between them is 4.22 times 10 to the 8 meters, but this is over r squared, so I'm going to have to square that part. I really recommend separating this part of each of the scientific notations from their exponents and calculating them separately. So I'll do that in blue right now. I'll just multiply the coefficients and divide the coefficients. And the value I got, remembering to square the 4.22, was 6.35. But it must be times 10 to the something. And the way you can solve that is you can take your negative 11 and add 22, and that of course is positive 11. And positive 11 plus 27 is positive 38. So I'll write that down just to keep myself organized. And then right here we have an 8, which is also squared. So this is actually 8 times 2, or 16. And that is in the denominator, so it would subtract from this. So I'm going to consider this a negative 16. So positive 38 minus 16 is 22, and it's positive. So my final answer is 6.35 by 10 to the 22 newtons, because this is a gravitational force. Now, as I said, we were going to reuse this value for FC. And we're actually solving for AC, which means that AC is Fc over m. And the centripetal force is going to be reused, as I said, so 6.35 times 10 to the 22. And we're going to divide that by the mass of Io. And Io's mass, I'm going to scan the question again. It was 8.93 by 10 to the 22. You can see these two parts will cancel, and we're essentially doing 6.35 divided by 8.93. And the value I got was 0.711 meters per second squared. You might also notice, if you're a super genius, that when you divide a force, which is newtons, by a mass, which is kilograms, that it wouldn't seem reasonable to get a unit of meters per second squared. So if you wanted to give a unit of newtons per kilogram to this as well, that would also be correct. And essentially what you're seeing here is that the magnitude of acceleration due to gravity is equal to another concept, which is gravitational field strength. Acceleration due to gravity is measured in the unit meters per second square, but gravitational field strength is measured in the unit newtons per kilogram, but they're equal in size, they just have different units. It's sort of like how impulse and momentum will be equal in size, but with different units. So 33 looks like it could be a friction question. But we see a horizontal force of 8 newtons is used to pull a 20 Newton wooden box moving toward the right along a horizontal wooden surface, as shown. It doesn't say it's moving at constant speed, which I'm just pointing that out. But it does want us to calculate the magnitude of the frictional force acting on the box. So we're going to have to do this the good old-fashioned way, since it's not moving at constant speed. So the frictional force is mu times Fn, and since we are solving for frictional force, we just need the mu for wood on wood. And this is moving, so it's going to be the kinetic mu that we need. And that value is 0.3. The normal force of this box is equal to its weight, which is 20 newtons. So 0.3 times 20 is 6 newtons. It says that we need the magnitude of the frictional force, but not the direction. But it's going to be this direction, so I'll just go ahead and write to the right because I like to report my forces in vector format. And that concludes this lesson. I'll scan through the answer choices for you just so that you can see them. And of course, let me know if you find any mistakes. Thank you for watching, and I hope this prepares you well for your exam, but definitely do some studying on your own. I want you to get a 100 on this exam.